Mount Etna is currently sliding into the Mediterranean Sea at a rate of about 3 to 4 centimeters a year.
Which is, already a pretty alarming detail on its own.
Right. But that's not even the weirdest thing about it. According to newly released data, Europe's most famous, most active volcano shouldn't even exist where it does.
Yeah, it really defies expectations.
Usually when we talk about geology or any hard science, really, there's this expectation of precision. You look at a map of tectonic plates, you see the lines where they meet, and you can point and say, right there, that's where a volcano goes, and here's exactly how it works.
We certainly prefer the natural world to be categorized neatly into rule books we can understand. I mean, it makes us feel safe.
Totally. But then you step into the shadow of a giant like Mount Etna, and suddenly that neat little rulebook is thrown completely out the window. We're looking at a geological landscape that is, well, completely baffling. It refuses to do what it's told.
It is a geological rebel, for sure.
And that is exactly what we're looking at today. We've got a fascinating stack of your sources right here, ranging from brand new 2026 geological research papers to high-tech geodetic analyses and deep earth volcanological reports.
There's some incredible data in this stack.
Our mission for this deep dive is to figure out what is actually happening under Sicily. We're going to explore how Etna has been secretly breaking the fundamental laws of plate tectonics for 500,000 years, what really caused its explosive outbursts in 2021, and how this mountain is somehow providing the blueprint for building a human habitat on the moon.
It is quite the narrative arc. I mean, we are starting deep within the Earth's mantle and ending up in lunar orbit.
Okay, let's unpack this. Because to understand why Etna is such a paradox, we first have to understand the normal rules of volcanoes, the recipes that Etna absolutely refuses to follow.
Right. Well, for decades, volcanologists have used three standard models to explain the formation of almost every volcano on Earth. First, you have divergent boundaries.
Like the Mid-Atlantic Ridge, right.
Exactly. Tectonic plates pull apart, the underlying pressure drops, the mantle melts, and magma naturally rises to fill the empty space.
Makes sense. Pull the crust apart, the liquid stuff below comes up.
Yeah. The second model is convergent boundaries, or subduction zones. This happens where two plates collide and one is forced underneath the other.
And that gets messy.
Very. As that bottom crust dives deep into the Earth, it drags an ocean's worth of water down with it. That water chemically lowers the melting point of the surrounding mantle, creating highly viscous, sticky magma.
Oh, wow. I never realized the water actually changed the melting point.
Yeah, it's a huge factor. And that magma fights its way up to form inland volcanoes. Mount Fuji in Japan is the textbook example.
Right. They usually form that classic cone shape, and they sit a good distance away from the actual fault line where the plates are colliding.
Correct. And the third mechanism is the hotspot model. This is where a massive, deep-seated thermal plume of superheated rock punches straight up through the middle of a tectonic plate.
Like it completely ignores the edges and boundaries.
Precisely. That thermal blowtorch is how you get the Hawaiian Islands, or, the supervolcano under Yellowstone.
Okay, so those are the three standard recipes. You pull the plates apart, you slide one under the other, or you have a giant deep earth blowtorch punching a hole.
Those are the big three, yeah.
But when I look at the maps and our sources, Etna is just sitting out there mixing up all the recipes. It's located right where the African plate is colliding with and sliding under the Eurasian plate.
Right on the boundary.
But it isn't inland like Mount Fuji. It's sitting right smack on top of the collision zone. So shouldn't it be a subduction volcano?
You would assume so, based on its location. But the chemical fingerprint of Etna's lava tells a completely different story. Its lava is classified as alkaline sodic.
And what does that mean exactly?
In the geological rulebook, alkaline sodic magma is the distinct chemical signature of a hotspot volcano. It implies a deep mantle source.
But wait, if it has the chemistry of a hotspot, there should be a massive heat plume melting the rock underneath it, right?
You would think so.
Because I was reading the seismic scans provided in these 2026 reports, and they are incredibly clear on this point, there's absolutely no thermal mantle plume beneath Sicily.
None whatsoever. The mantle there is actually relatively cool compared to a hotspot.
If there's no massive heat plume underneath it, where is all this hot spot lava coming from? It's like finding a geyser in a desert.
It really is a paradox.
And it's not a small amount of lava either. Etna is one of the most prolific lava producers on the entire planet. So how is it making all this rock?
What's fascinating here is that this exact contradiction forced the scientific community to abandon the old labels entirely. The 2026 research finally gives us the answer. Mount Etna isn't actually a melt generator.
Wait, really? What do you mean? It doesn't make its own magma?
Exactly. Well, to be precise, it acts as a magmatic conduit. It doesn't use localized heat to melt new rock into magma.
Oh, I see.
Instead, it acts as a structural leak for ancient, pre-existing melt that is already sitting deep within the Earth.
So if there's no heat melting the rock, what physical force is actually pulling the magma up to the surface? Where is it stealing this pre-existing melt from?
To answer that, we have to travel 80 kilometers straight down into the Earth to a layer called the low-velocity zone, or the LVZ.
Okay, 80 kilometers is deep.
Very deep. The LVZ is a boundary layer located between the rigid, rocky tectonic plates above and the hotter, more fluid asthenosphere below. It's a mushy global layer that already contains between 1 and 5% liquid melt.
So it's always just sitting there kind of slushy?
Exactly. Normally, that liquid just sits there, completely trapped and pressurized by the immense, crushing weight of the tectonic plates resting on top of it.
But Sicily, as we've established, is not a normal place tectonically.
No, not at all. To understand the physical force driving the magma upward, we have to scale up a phenomenon called petit spot volcanism.
Petit spot. I read about that in the sources.
Yeah, this was first discovered back in 2006 near the Japan Trench. Scientists found these tiny submarine knolls, maybe a few hundred meters high.
So pretty small.
Right. They form when a tectonic plate bends as it prepares to dive into a subduction zone. The flexure, the physical bending of the solid rock, causes the bottom of the plate to crack.
Ah, okay.
And that bending action literally squeezes the pre-existing liquid melt right out of the mushy LVZ below it.
Hold on. I can visualize that for a tiny little underwater bump. But petit spots are minuscule. Etna is an absolute giant. It's over 300 meters high.
It is massive, yes.
If the plate is trapped under the weight of an entire continent, how does a simple bend in the rock squeeze out enough magma to build a mountain that massive?
And because the African plate isn't just bending smoothly, it's caught in a violent, messy process called the Ionian slab rollback.
Slab rollback, that sounds intense.
It is. The plate is stuck, it's folding, and it's tearing. There's a massive geological feature driving this called the Malta escarpment. In tectonic terms, it acts as a step fault.
The sources refer to that acronym a lot, a subduction transform edge propagator. But what does that actually look like deep underground?
Well, imagine a thick, stiff piece of cardboard. If you push one side of it down into a slot, the whole thing eventually buckles and rips.
Oh, I see the picture now.
A step fault is that rip. It creates a slab window, a literal tear or gap in the Earth's crust. Because the African plate is bending and ripping at the same time, it creates intense tensional stress.
So the plate is tearing open.
Yeah, think of the tectonic plate like a giant, dense sponge resting on top of that mushy, liquid-rich LVZ. The extreme flexure of the plate literally squeezes the pre-existing volatile-rich melt out of the LVZ and forces it up through that physical tear in the crust.
It's not like a boiling pot boiling over. It's more like a sealed juice box. If you squeeze the box hard enough, the juice is going to find the weakest point, in this case, that torn slab window, and shoot right out the top. Etna is just the straw.
That is a brilliant analogy.
Yes.
The mechanical failure of the tectonic plates themselves is what is driving this volcano, not a thermal heat plume. It is purely tectonic-controlled volcanism.
That completely flips the script. But if Etna is basically a giant squeezed leak acting as a straw, that straw has been sitting there for 500,000 years. Has the flavor of the juice changed over time?
Drastically. If you look at the isotopic evolution of Etna's lava over the last 500,000 years, you see a distinct maturation of this conduit.
Maturation, like it grew up.
Basically. Early in its history, the magma that was squeezed out of the deep LVZ had to fight its way up through a very thick, chaotic layer of continental crust.
So it was picking up hitchhikers along the way, absorbing other minerals from the crust.
Exactly. The magma reacted heavily with the crust, resulting in what we call silica-rich or tholeiitic lava. It was heavily contaminating.
Okay, so what changed?
Around 330,000 years ago, a major transition occurred. The continued squeezing and erupting basically cleared the throat of the volcano. The pipe became well established. It matured into a direct, unadulterated conduit.
Meaning the primitive deep earth magma from the LVZ could finally reach the surface without getting chemically altered by the shallow crust.
Yes. And the geological proof of this is in the isotopic stability of the recent lava.
Right. The sources mention the ratios of strontium and neodymium. Why do those two specific elements matter so much?
Because crustal rock is incredibly messy. It has been weathered, recycled, and churned up over billions of years, so its isotopic ratios fluctuate wildly.
Just a total mix of everything.
Yeah. But the deep mantle, the source of the LVZ, is pristine and stable. When scientists test the strontium and neodymium in Etna's modern lava, the ratios are stubbornly perfectly stable.
So it's a direct match.
It is the undeniable chemical fingerprint of the deep mantle. It proves the magma is coming from a permanent, deep-seated reservoir, not a shifting, shallow subduction source.
Here's where it gets really interesting. If this pipe is basically a direct straw going 80 kilometers straight down into the pristine mantle, shouldn't we see some massive physical evidence of that on the surface, even when there's no lava flowing?
We do. And it's invisible to the naked eye. The evidence is in the gas.
Right. Etna is an incredibly heavy breather. The data shows the single mountain emits a staggering 13 million tons of carbon dioxide annually.
Which is a profound volume of gas, just mind-boggling.
It's completely excessive. The research points out that this is way more CO2 than the actual erupted magma could physically hold.
Exactly.
Which implies that even when Etna is quiet and not erupting lava, it is acting as a permanent, open chimney, venting gases straight from the deep earth into our atmosphere.
Volcanologists call this open conduit degassing. The LVZ is rich in volatiles, elements that easily vaporize, like CO2 and water.
So they just boil off.
Sort of, because Etna's matured pipe is essentially a clean fracture down in that deep zone. Those gases constantly separate from the deep magma. They're light enough to bypass the heavy rock in the pipe and leak continuously to the surface.
It functions as a steady exhaust valve for the planet.
That's a perfect way to look at it.
Okay, so we have this open exhaust valve steadily breathing out gas. But what happens when that valve gets blocked? When the dense magma acts like a plug and the deep gas gets trapped? That brings us to the explosive, violent events of 2021.
To understand the 2021 eruptions, we need to look at the mechanical physics of Etna's plumbing. Specifically, the Ferlito model from 2018.
Okay, I remember reading about that.
The magmatic column inside Etna is not just a uniform solid tube of glowing rock. It operates as a dual-phase fluid flux.
The two-part engine.
Deep down in the system, you have what's called the WMS, the water melt solution. This is a supercritical fluid.
Supercritical, so it's not really a liquid or a gas.
Right. It's essentially 70% gas by volume, mostly highly pressurized water vapor and CO2, with some basaltic components dissolved inside it. Because it is predominantly gas, it has a very low density, roughly 1,140 kilograms per cubic meter.
So it's incredibly buoyant. It violently wants to rise to the surface.
It does. But sitting above it, at the top of the volcano's plumbing system, is the CMP, the continuous melt phase. This is a degassed, heavy basaltic plug.
Because the gas already escaped.
Yes, because all its gas has already bubbled out and escaped into the atmosphere. The rock that's left behind is incredibly dense, around 2,800 kilograms per cubic meter.
That is over twice as dense as the fluid below it. So basically, it's a giant geological pressure cooker. You have this highly pressurized, super light gas at the bottom, and it's physically trapped under a heavy, viscous rock lid at the top.
And normally, if that heavy CMP plug remains somewhat warm and fluid, the gas bubbles from below can just slip right through it and escape.
That's the steady open conduit degassing we just talked about.
Exactly. But if that heavy rock lid cools and becomes too viscous, or if there's a sudden massive surge of highly pressurized gas squeezing out of the deep LVZ, the pressure inside the mountain begins to build dramatically.
And we can actually watch that pressure building, right?
Yeah.
The sources talk about tracking it with GNSS. I understand that's basically GPS, but how does tracking a signal from a satellite tell us what's happening under miles of solid rock?
Global Navigation Satellite Systems, or GNSS, along with ground tilt meters, track millimeter-scale changes in the physical shape of the mountain.
The mountain physically changes shape.
It does. When the pressure builds, the solid rock of the volcano actually swells and deforms like a balloon. From 2019 to 2020, these instruments tracked the center of that pressure deepening, moving from 2.1 kilometers down to 5.7 kilometers below the surface.
So it's backing up.
The volcano was accumulating a massive, deep reservoir of this highly pressurized WMS gas. Then, just 2 months before February 2021, the data shifted violently. They recorded a fast-ascending source rocketing up to just 2.0 kilometers beneath the crater.
The pressure cooker was redlining. The gas was making its move.
The buoyant, highly pressurized WMS fluid completely overcame the structural weight of the heavy CMP rock plug. The result was the February and March 2021 sequence. 17 highly intense paroxysms.
17 massive fire fountains blasting molten rock into the Sicilian sky in just a matter of weeks. The sheer mechanical force of that is terrifying.
It was a spectacular and violent release of energy.
And the aftermath of that pressure release is just as wild. The sources state it caused the most intense deflation in 2 decades. The edifice of the mountain contracted so violently after releasing that gas, it actually pulled the entire eastern flank of the volcano backward.
If we connect this to the bigger picture, eruptions at Mount Etna aren't just thermal events where rock simply gets hot and passively overflows. They are violent structural mechanical failures of this dense magma plug.
So it physically inflates as the deep gas pressurizes.
Yes, and it snaps back when that pressure forcefully blasts the lid off.
Knowing that Etna is fundamentally a mechanical pressure cooker changes everything about how we interact with it, especially when you think about how we protect the 500,000 people who live right in its shadow. If the magma can shoot up from 80 kilometers down, we can't just look at the surface anymore.
The scientific understanding of the leaking pipe requires a total shift in hazard monitoring. Shallow crust monitoring is no longer sufficient. Scientists now have to hunt for deep precursors. They're trying to find the pulse of the LVZ.
One of the metrics they use is called a B-value drop, which sounds like abstract math, but it's actually about earthquakes, right? How does a B-value drop tell us the deep pipe is pressurizing?
A B-value drop tracks the frequency and size of earthquakes. When deep, highly pressurized fluid pushes up from the LVZ, it forces its way into microscopic cracks in the surrounding rock.
Okay, getting into the piney faults.
This fluid acts as a high-pressure lubricant. Instead of the massive tectonic plates catching, building up immense tension, and snapping in one huge destructive earthquake, which would register as a high B-value, the lubricated rock slips continuously in thousands of tiny, microscopic tremors.
Oh, wow. So an increase in tiny tremors and a drop in future quakes means the fluid is actively rising and greasing the faults.
That's right. And they're also tracking the gases to see when fresh magma arrives, checking the CO2 to SO2 ratios.
Why those two gases?
Because CO2 comes from much deeper in the mantle. A sudden spike in CO2 means a fresh batch of buoyant magma has just rushed up from the LVZ.
They monitor all of this while also watching the physical structure of the mountain. You mentioned earlier that the mountain is sliding into the sea.
Yes, which is a massive geological hazard on its own.
Right. I read about the RV Meteor research crews. They took submersibles and mapped the underwater flank of Etna, and they found fresh lava 1,000 meters deep in the ocean. The entire southeastern flank of the mountain is slowly sliding toward the sea.
Which is a critical factor because that continuous sliding is what keeps the fracture network, the step fault, pulled open. It physically maintains the leaking pipe.
So if it stopped sliding, the pipe would close.
Very likely. If the mountain stopped sliding apart, the incredible weight of the crust might seal the pipe entirely.
So if we are monitoring these deep earth precursors with all this advanced technology, what is the end goal? Is it just to warn the surrounding towns, or are we actually learning how to utilize this bizarre mantle rock? Because the craziest part of all of this to me is how this tectonic anomaly in the Mediterranean is actively helping us build habitats on the moon.
It is a remarkable leap, but a very practical one. Because Etna's leaking pipe delivers materials directly from the deep mantle, without the magma heavily reacting with the shallow crust, the lava it produces is incredibly unique.
It's the pristine stuff.
Exactly. When it reaches the surface and cools, it contains a 40% amorphous phase.
Amorphous meaning it cools so rapidly it lacks a rigid internal crystalline structure. It's essentially volcanic glass.
Yes. And structurally and chemically, that amorphous volcanic glass mimics lunar impact glass almost perfectly. The moon's surface is covered in soil created by meteorites superheating rock into glass. Etna is currently the premier terrestrial lunar simulant.
It is naturally occurring fake moon dirt.
Basically, yeah.
So instead of flying to the moon to test our equipment, space agencies can just go to Sicily. How exactly are they using this Etnian rock to prepare for a lunar base?
Scientists are using these Etnian alkali-activated materials to test in situ resource utilization technologies, or ISRU.
ISRU, living off the land.
Right. If humanity is going to sustain a moon base, we cannot afford to launch thousands of gallons of water and breathable oxygen from Earth. It's too heavy and expensive. ISRU hardware is designed to extract oxygen and water directly from the lunar dirt.
How do you get breathable oxygen out of solid rock?
By superheating the simulated Etna rock and passing highly calibrated electrical currents through it, this process physically strips the oxygen atoms that are chemically bound within the silicates of the rock.
That is incredible.
They are perfecting this extraction method on Etna's lava right now. Furthermore, they're using the leftover material to 3D print structural bricks. Tests show that construction materials made from Etna's lava have compressive strengths of 16.40 megapascals.
Megapascals are a little abstract for me. How strong is that in real-world terms?
To put 16.40 megapascals in perspective, that means materials made from this magma are just as strong as the commercial load-bearing concrete we use to pour the foundations of heavy buildings here on Earth. They're incredibly durable.
It just blows my mind. You listening to this, think about that. A tectonic glitch, a mountain that has been terrifying and mesmerizing humanity for thousands of years, a literal tear in the African plate, is currently the testing ground for the technology that will allow us to survive on another celestial body.
This raises an important question. How many other terrestrial anomalies might hold the key to our extraplanetary ambitions? Understanding the deep mechanical forces of our own planet at a local level is directly accelerating our ability to leave it.
So what does this all mean? We started this journey looking for rules, for precision, for clean boundaries on a tectonic map. Instead, we found a leaking pipe connected 80 kilometers straight down into the deep mantle.
A completely different mechanism entirely.
Yeah, we found a mechanical pressure cooker driven by a dual-phase engine of light gas and heavy rock. And we found a direct gateway to lunar exploration. It means Etna is a machine driven by the relentless bending, tearing, and squeezing of tectonic plates. It completely rewrites the rules of geology.
It forces us to reconsider the ground beneath our feet. And I leave you with this thought. If a massive, world-famous 3,400-meter giant like Mount Etna managed to hide its true, bizarre origin from human science until the year 2026, what other fundamental tectonic rules are currently being broken by landscapes we think we completely understand? What other deep earth sponges are being silently squeezed beneath your feet right now, just waiting for the pressure to become too much?
It really makes you look at every mountain, every fault line, just a little bit differently. The rulebook is never fully written. Thank you so much for bringing such an incredible stack of sources for this deep dive. Until next time, keep questioning what you think you know.